Hello, everyone, and welcome to the channel Mathemagic Notes. So, today, the topic on which I will discuss is symmetric and asymmetric matrices. So, let us just first of all focus on the topic symmetric. So, what do we mean by a symmetric matrix? So, let us just first of all focus that symmetric and asymmetric matrices are only, dealt when we have a square matrix. Okay, I hope so that you have gone through the previous lectures and what do we mean by a square matrix. It is nothing but if I have a, I'm just writing down the general form of a matrix Aij with the order Mn. And if we are dealing with a square matrix, then the order is in such a way that my n will be equal to n. So in general, if I were to write my matrix as, it will be Aij m cross m. So this is my square matrix. So this is the first focus which we need to pay attention to. Now the next important point is that in the previous lecture we focused on the transpose of a matrix, isn't it? What was it? My transpose was denoted by A dash, right? And what we do, we generally turn the rows into columns and the order is swapped. Okay, I hope so you have gone through the previous lecture. And if you haven't been through it, just go through the previous lecture of mine, which is part 4. Yeah. So now we know that we are dealing with a square matrix and a transpose. So a matrix is said to be symmetric. It is said to be symmetric if my A dash is equal to A. Now this is a very important condition. For my matrix to be symmetric, my A dash must be equal to A. Now, what do we mean by that? So let me just consider an example. So this is a 3 cross 3 matrix with elements in it. I'm just writing it down. So this is my 3 cross 3 matrix. Now, as an activity, just pause the video and find out what is my transpose. Just pause the video right now and find A transpose. I will just continue in a while. Yeah. So I hope so that you have calculated the A dash. So as per the rule, we know that we are converting each row into my column, right? So row 3, 2, and 3. Then my next is, this is my second row. This is 2 minus 1.5 and minus of 1. What is my third row? This is my 3 minus 1 and 1. So this is my transpose. Now just look at it carefully. Isn't it the same matrix which we have started with? My A dash is equal to A, isn't it? Just observe each and every entry. So this is what we mean by a symmetric matrix, where when we take the transpose of the matrix, it in turn gives me the matrix A. Okay. Now let us just focus on what do we mean by a skew symmetric. So in skew symmetric matrix, again we will just focus on a square matrix. There is no change in terms of the initial idea which we have discussed in the symmetric matrix. But the addition condition is that the transpose of the matrix is equal to minus of A. If you will just compare it with the symmetric case, it was A dash is equal to A, right? In my case of symmetric matrices, it was my A dash is equal to A. But in this case, skew symmetric, my A dash will be minus of A. So as an example, I will just write down an example. Again, I will be considering a 3 cross 3 matrix. So these are the entries, okay? Again, pause the video and find the transpose of this matrix. I will just wait till you do it. So you must have solved it now. So what is my transpose? The row becomes the column. Again with the second row. Sorry, this is G. And my third row. Now just observe that if you will observe my B dash is equal to minus of B. That is, if I multiply this matrix with a scalar minus of 1, and if I multiply this is nothing but my B dash. Okay, so this is the case of skew symmetric. So this is kind of a theory or something which you must remember. It is that the diagonal in a skew symmetric matrix, they are all 0. So what do we mean by that? As an example, which we have just discussed above, you can observe that in the matrix, the diagonal element was 0, isn't it? Each element in my diagonal was 0. So that is what we will be discussing it theoretically. So theoretically, we know that in a skew symmetric matrix, my A dash is equal to minus of A, isn't it? Now, if I were to write it in terms of Aij, this will be minus of Aji. Why? Because we know that in transpose, we swap the orders, isn't it? Swap means if my order was m cross n, my m goes to m and m will go to n. It is nothing but n cross m. So in a similar way, my Aij will become Ji, that too with a negative sign because we are dealing with a skew symmetric matrix. So if this is the case, now if I will put my I is equal to j, okay, because what we are dealing here with is a square matrix. So my I must be equal to j. It is a pretty common observation. So my ai must be equal to aii, okay, because I'm considering I is equal to j. Now I will just bring this aii over here. This is equal to 0. Now my twice of aii is equal to 0, which is nothing but my aii is equal to 0. Now, what is my AI? AI is nothing but my diagonal elements, which is A11, A22, A33, so on, depending upon the order which we are discussing. So that is the reason why my AII here was 0, A22 was equal to 0, and A33 was equal to 0. So this is a very important concept which you must remember at the back of your head. So let us now proceed to few more theorems based on symmetric and asymmetric. So this is my first theorem where we are, as usual, considering a square matrix. Now what it says is that my A plus A dash will always be a symmetric matrix and my A minus A dash will be skew symmetric. It will be my skew symmetric. Now, in order to check this condition, how do we relate symmetric and skew symmetric? It was by transpose, isn't it? Where if my A dash is equal to 8 meant that it is symmetric and if my A dash is equal to minus of 8 means skew symmetric. So let us just assume that my B is equal to A plus A dash. Okay, so I will just take the transpose of this. What will it be? A plus A dash dash. Okay, so this will be equal to, I will just open my bracket. Okay, so this will be the next step. So this, because I am dealing with using the property of transpose I have discussed in my previous lecture. Kindly go through it. It is in my previous lecture. That if I take the transpose of A dash, it will just give out to the original matrix which you have started with. So this will be A dash plus of A. Okay. Now if you will focus, this is B, isn't it? It means that A plus A dash is my symmetric. Okay. Now, on a similar basis, let us just try to prove that my A minus A dash is skew symmetric. So let us assume this is C. So I will take the transpose of this value. So this will give me A dash minus of A dash of dash. Okay. Now again, using the property which you have mentioned in the previous slide, that my A dash dash is A. So this is nothing but A dash minus of A. So let me just take the negative sign common. This will give me A minus of A dash, which is nothing but minus of C. So we can see that if I take the transpose of this, C, it is coming out to be minus of C. So this theorem is proved that A plus A dash is my symmetric and A minus of A dash. Now this is the last theorem based on my symmetric and skew symmetric matrices. Now what does this say is that we are again starting with my square matrix. So this square matrix can be expressed as the sum of my symmetric and skew symmetric matrix. Now what do we mean by this is, if I'm considering a matrix A, a square matrix A, and so let us just try to involve the concept of symmetric and skew symmetric in such a way that it will just in turn give me back my matrix A. How can we do that? Uh, for a symmetric, we just proved that my A plus A dash was my symmetric part. Okay. Let me just put a plus sign and with some gap. What was my skew symmetric part? A minus of A dash. Now, what can we do in such a way that this totality, this sum can give me my A is that just simply putting a half, multiplying both the terms by half. Now, just cross check. Is this term giving me back my A? So yes, this is in turn giving me back my A. This was minus of half plus of A dash of A dash by 2 plus of A by 2 minus of A dash by 2. So this is nothing but this term will cancel. This is my A. So this theorem is very important because in the next lecture I will be discussing a question based on this question, the theorem, where I will be expressing my matrix in as a sum of symmetric and skew